everyone. Can someone confirm whether I am audible clearly or not? Yeah, thank you. Okay, fair enough. Let's get started. I think due to some link related issues, there is a slightly delayed start, but let's try to manage it out. Let me share my screen. I think it's already shared. Okay. Okay. So in the last two sessions, we have looked at natural language processing, wherein some kind of text data, analyzing the text data, etc., have been taken up. Now, the next major area that I'm going to look at, we have two more topics to look at. One is talking about the time series analysis, which we will do probably in the today's session and some part of the next session. And just giving you a very brief intro into the world of image, right? How do you really, so this is a time series data. Earlier we looked at the textual data. So a little bit of handling of the image data also is something that we will look at if the data is in the form of images, etc. So that exercise will take up in our next class. So probably within another two sessions or at the max 3 sessions, we would be winding up this course overall. We have gone slightly more than the number of hours that we have initially specified. I need to get an information from Ravindra in terms of how many hours we have typically went ahead, but definitely I could see that we have exceeded the initial promised number, which means definitely you will get access to all these videos and the Python notebooks so that you can actually practice on them. But of course, whatever we are dealing in the last few sessions, including the natural language processing, we are not going in those areas in depth. Each one can very well be converted into another 20 to 25 hours kind of sessions, or probably much more than that also in some areas. And these are all different areas where you can master and become experts also. And all these, somewhere or the other, they will lead towards usage of your machine learning techniques. As we have seen in textual data, once you are able to convert the text into bag of birds at frequency or TF-IDF, you can very well convert that into a kind of a machine learning problem. Now, similarly, we would be seeing with respect to the image also, possibly in the next class. In the current class, we would be looking at a data that is available in the form of a time series. Obviously, people who have done CS2, either past CS2 or preparing for CS2 or something, you have a very detailed 2 chapters with respect to time series analysis, right? So what we are going to talk about now, if people don't have too much of an idea about CS2 or have not looked at CS2, then possibly you should look at the trainings that are being offered for CS2, or do some kind of a basic preliminary workout, because here I'm only giving an introduction of how you are going to work with the time series data. What are the things that you would like to do with the time series data? Especially when you look at the applications wise, you can very well see any kind of financial assets and their prices, right? So you can forecast the prices. or you can think of sales, monthly sales, weekly sales, forecasting of the sales, or I can think of even the forecasting the lives, right? I can very well use the time series analysis. I mean, of course, here it's just not a time series analysis. You may have to probably link it up with some amount of cross-sectional also. So probably this might very well go towards a combination of time series and cross-sectional, which could be like a panel data analysis. That is what you can typically call as age period cohort or age period cohort kind of a models, right? So I mean, you can very well look at various applications of the time series analysis. Okay. Now, so what is the time series? Wherever the data is there, any data, if it is there in the form of associated with some time element. So it could be an element with respect to a date, or it could be a daily or weekly or hourly or monthly. All these kinds of data are typically called as time series data. Now, if I do the, if I say I want to build a model, I want to build a model for forecasting future value based on the historical values, right? I want to do a forecasting of the future values based on the historical values. That is what we call as the time series analysis, right? You are forecasting the futuristic values based on the historical value. So if I use the historical values of the same variable, then it becomes a univariate time series analysis. And if I use the historical value variables of the same variable along with some other variables, then it becomes a multivariate time series analysis. Right? I'm not only using the historical variable values of the current variable or the target variable, but I'm also using the historical values of the other variables as well. Then it becomes a multivariate. Now, this time series can be analyzed again using the typical statistical approaches, or it could very well go with a machine learning or a deep learning kind of approaches as well. Right? So which means you, if you want to use a kind of a machine learning approach here, you just need to convert the problem. You just need to convert the problem Yeah, if you want to use machine learning, you just need to convert the problem into a target variable and set of feature variables. Once you convert, you can very well use any of the machine learning models on the top of it. Whereas the statistical models, probably in your CS2 course, you would have really gone through using autoregressive or MA, which is the moving average, or using an ARMA, auto-regressive moving average kind of model. So all these models, they really help us in statistically establishing a relationship between the target variable and the historical values of the target variable, which are your explanatory values. So if I'm talking about one process, which is, let's say, I'm talking about a stock price at some time t, if I express this stock price at time t in terms of the stock price at time t minus 1, stock price at time t minus 2, and so on. Stock price at time t minus p. This is typically called as an auto-regressive process of order P. So which means that today's value, the Tth period value of the stock price or any such kind of time series variable is expressed in terms of its historical value. So this becomes a auto-regressive kind of a process plus some delta. Similarly, if this y t can be expressed in terms of some constant plus the error terms of the previous historical lags, then this is typically called as the moving average process, moving average of the typical error term. So this is a moving average of the order Q. Then I integrate these two things. Then it can become an ARMA process of order P comma Q. Now there are various ways to identify. This is a statistical approach, very good kind of an approach, right? And we have various mechanisms in which we can evaluate what is the value of P and what is the value of Q that are more and more appropriate for a particular prediction problem. And we also discuss about some of the concepts. I'm not going into each one of them. So some other concepts that we deal with in time series are looking at the stationarity of the data, looking at the presence of autocorrelation. These are some of the common topics that you really get into. You use something like an autocorrelation function or a partial autocorrelation function to decide also whether autoregressive models or moving average models or a combination of autoregressive and moving average model are required for modeling the relationship between a time series variable and its historical value. So all this conceptual part is there for you, especially if you are a member of IAI. Probably your CS2 course curriculum would typically be considering these topics. You may have to read through now what does the stationarity mean. So if I consider any process, then the mean of that process at any time point should be a constant, right? The mean should be constant with time. The variance should be constant with time. The autocorrelation should be should be dependent only on the lags and does not depend on the specific time period. And from there, you also understand another process called a white noise process, a Gaussian white noise process. I don't want to get into all those because I'm not covering the theoretical aspects here. I am going to talk about if I want to really take up a use case regarding prediction, right? Let's say I want to predict the stock price. I want to take up a problem of prediction of the stock price. Let us see how good is our model to predict the stock price. That is a kind of a problem that I want to take and I want to handle. Okay. So I'll get started. If anyone has any kind of query before we get started, please let me know. So here what I will do is, probably we'll go with your example. One of you can talk about one stock price, one stock, we will download the data and we'll see how do I predict. So I may look at the stock price for that, and I would also look at the stock return. Let us see. You give me any stock of your choice, the first response that I get, I will pick that up, and we will see whether it is really possible to predict the stock price or not. How comfortable using the ARIMA model, how comfortable it is to predict the stock price, and if at all we are able to predict the stock price, what would be the error associated with it? Okay, briefly explain stationarity. Okay, in the meanwhile, I'll just spend a few minutes. Right, probably look at data something like this. Right, this is a typical data across time. Now, in a very simple language, if I have to take, randomly you take any two data points, any two intervals, equal intervals at any two time points, right? So, if I typically look at the mean value, right? So, if I say this is the mean of these values here, and if I talk about this as the mean of values, statistically, these means should be equal. So, which means the expected value, right? Expected value, which is the mean, is always constant in a time series, in a stationary series. So, the opposite of stationarity is you have some kind of a trend, something like this. So, if I take at this point versus at this point, the average typically is not the same statistically because there is an uptrend here. So, when there is an uptrend or a downtrend, you don't find the series to be stationary. So, the first condition that I require is the expected value of a series at a particular point in time that should be more or less constant. So, more or less is nothing but statistically that should be equal. The mean should be equal. Similarly, if I take the variances also, the variances also should be constant at any point in time. So, if the variances are constant, it is typically called as homoscedasticity. And if the variances are different at two different points in time, that situation is called heteroscedasticity. So you will have to handle that heteroscedasticity by using some kind of Garch family of models. So that is what we typically called as volatility modeling, which we are not dealing here. And the third important concept that requires is you take the autocorrelation. So you find out the autocorrelation at any lag. So probably you take the autocorrelation with a lag 1. Lag 1 means you talk about, if I have to put it in simple words, let's say I have the data from 1 to 500 days of data, right? So if I am taking the data typically from 101st day to 200th day, that is one subset that I took. And another subset that I took is 401st day to 500th day. Right? These are the two subsets. I'm just giving in a simple layman example. So, the lag, when you are saying lag 1, autocorrelation, what you will say 101, 102 and 200. This is one data. Probably you take it with a lag of 1. Right? So which means here you will not have any value. Here you will have 101st value. And here you have 199th value. So which means you take the correlation between these two. These are the dates. 102nd day's value to 200th day's value. And on the other side, you will have 101st day value to the 199th day value. This is called autocorrelation at lag 1. Similarly, on the other side, I can also take on the same lines, I can start from 402th value to 500. And I would put a 400 first value to 499, and I'll also take another auto correlation with lag 1. Now, these two lag 1 correlations, they should be constant, again statistically, right? Which means there should not be a significant difference. You can use that p values of the t-test and things like that. So similarly, lag 2 correlations. So I have just taken only two subsets, but any subset that I take, any subset of any size that I take, for a specific lag, the autocorrelation will be constant. So if any particular series satisfies those three properties, we say that it is stationary. Now, there are ways of checking for stationarity practically. We don't do all this. We have a few tests. One is called as augmented Dickey-Fuller test, which is actually doing the testing for what is called as unit root against a non-unit root, which can have a possibility of a stationarity. Or similarly, you have a KPSS test, or you have something called Phillips-Perron test. So there are different such kind of tests which can help us in testing whether the data is stationary or not. Now, the next thing, why do I really need to check for stationarity of the data? So that is actually associated with what is called as a Wolt's theorem. So any stationary data, what that theorem simply says is any stationary data can be expressed. Any stationary data can be expressed in the form of historical observations and or historical error values. So, which means I can very well model any stationary series, right? I can model any stationary series by using the historical observations and historical error. That is what is the starting point for the usage of the ARIMA model. So ARIMA models, definitely the ARMA, the auto-regressive and moving average model, they definitely require the series to be stationary. Does that answer your question? Who has asked it? Let me just check it. Shubham? Any specific area you require? Probably you let me know. Okay, partial ACR. So, I mean, again, I'll use a very common man's language rather than getting more technical, right? So, possibly, if I'm using ACF, you could clearly see here. So, I'm looking at, let's say, the correlation between YT and YT minus 1. This is called lag 1 correlation. YT and YT minus 2, this is called lag 2 correlation. YT and YT minus 3, this is called lag 3 correlation, right? Now, these three values could be much, much higher. So I can say the autocorrelation is significant at the top 3 lags. But if I go internally, when I look at YT and YT minus 2, they may be correlated very much. But this correlation could be very much moderated by YT minus 1. So this correlation could be higher because probably YT minus 1 and YT minus 2 are well correlated, and YT and YT minus 1 are also well correlated. So that will, these two are like two first degree correlations, first lag correlation, right? So what we say is, in partial autocorrelation, I try to remove the impact of YT minus 1. So what is the correlation that is contributed by YT minus 2 alone, removing the impact of YT minus 1? So that will become the partial autocorrelation, which means obviously I know YT is correlated with YT minus 1. But if I have to use YT minus 2, there should be some additional information in YT minus 2 which is not provided by YT minus 1. And that is typically called as the partial autocorrelation. Right? I'm looking at removing the impact of the first lag and try to see what is the exclusive contribution between YT and YT minus 2, ignoring the impact of YT minus 1. So which means the better way to do that, I mean, technically what you do is you run a regression between YT, you run a regression between YT minus 1, YT minus 2 and so on. And the regression coefficients of YT minus 1, YT minus 2 is what will give you the coefficient. So which means if those coefficients are significant, you say that your team, I mean, there is a partial autocorrelation up to this specific class. So in another word, we are simply looking at the exclusive contribution of the value at a higher lag without having any kind of involvement of the intermediate lags. Does that okay? Does that sound good? Yeah. So which stock do we try to predict? Probably that should be interesting for me as well. Probably we'll try. We'll take one stock and we'll see if there is any possibility of prediction or not. So we can take one stock, which we will experiment the end-to-end step. We can see at least by using the basic time series model, to what extent the stock prices can be predicted, what is the kind of uncertainty with respect to their prediction, things like that. You can give me one stock, otherwise I'll take something. Okay, otherwise I'll pick up one stock, let's say Reliance Industries or Infosys, will take something like that. So here initially, the good thing that I want to talk about is something like Yahoo Finance. It actually provides historical stock price data of a very good number of stocks across the world, not just limited to India or US, probably a good number of stocks, of course, or we'll take Bitcoin to get some more interest into the problem, right? So we will try to predict the future price of Bitcoin. Okay, using the time series analysis. So I'll try to get the data from Y Finance. Y Finance is a kind of Python library which can help us to extract the data from Yahoo Finance. Then this is a PMD ARIMA is another interesting function which actually helps us in automating the entire auto regressive moving average, whatever. That's one full chapter in CS2. Right, if I say, if I talk about CS2, one full chapter talks about the autoregressive, the stationarity, autoregressive, moving average, autoregressive, moving average, all these kinds of concepts. Now, what you generally see is if I use this particular library called PMD Arima, all this activity is done in one single step. The whole 14th chapter is handled in one single step, right? Probably you may spend more time on interpretation, but definitely the working out time is very, very low. All the mathematics is taken care of here. So that's where when I do something on a practical basis, I may not want to explain all the equations, theory, and all those things. But yeah, wherever required, we should definitely try to understand that part. So I will install these two libraries because they do not come as the default implementation of the Google Colab. So I will now after that I'll see Matplotlib. These are the default libraries that you have to import every time. But along with that, I am also importing something called Y-Finance, which is actually a kind of a library which deals with connecting to Yahoo Finance to obtain the various data. So I'll take this. Now we will take the data, let's say for the last 5 years. Let's not take for longer period. Probably let's say from 2017 December 31st is what I want to start this data. Right, by that time the Bitcoin would have been matured, or probably will go a little bit more, let's say 2015 December. So from 16 onwards is what we are collecting. 16, 17, 18, 19, 20, 21, 22, almost 7 years of data. So we will look at it. Probably I haven't also looked at it, so which means it would be equally interesting for both of us. So if I want to know how do I download, this is actually a Nifty. This code is for Nifty, but we will have to look at for Bitcoin. I'll just look out for Bitcoin there. If it is available, then we'll pull it. Otherwise, we'll take something else. Yeah. Yeah, BTC hyphen USD. That is the code. BTC hyphen USD is the code for Bitcoin. Okay. So I will download this data. We'll go only with one. I'll download this data. So if you really look at printing it, you'll see that the values are available. Okay, the Okay, I did not run this start date. Now I'll download it again based on the start date. Now you could see December 31st, 2015. So these are the values that the Bitcoin is there. So it all was started almost at 400 in 2016, but now at the current moment it is almost at 28,000. And this is how the volume of the transactions are also there, right? So probably I would simplify the whole problem. Okay, let me do. In case you want to download a date, this is a daily data, right? But let's say you want to download the Bitcoin on a monthly basis. Let's say you want to download the Bitcoin on a monthly basis. All you interval is 1 month. So you can very well give different intervals, and accordingly you can download data as well. So if you really look at this, you will see that you can download the data even on a monthly basis. So especially if you are having some kind of stocks or financial assets, and you need the prices of those financial assets, then you can very well download the data from Yahoo. So you could because only those many months. Whereas on a daily basis, you had almost 2,647 rows of data altogether. Okay. So if at all there are any missing values, because sometimes what could happen is countries have different holidays at different points in time. Sometimes Yahoo Finance will not be able to fetch the data when the markets are typically closed on that day. This might be more in the case of stock markets, etc., where you find the markets are closed on some of the days. And for some festivals or something, if the markets are closed, then Yahoo Finance, probably because it operates, let's say, US or something, which is holiday on that day, you find that the date would exist, but the values would not exist. So in that case, the values could still be shown as NA. So that's where what we say is whatever is the data that we collect from Yahoo Finance, better you say if there is a blank value, drop it. So both in case of daily data, DF was what I have called for daily data, and BF1 is what I called for monthly data. Whatever is the data, just remove the blank because that would cause a kind of a problem for us. And we can very well say the blanks are primarily, there could be various other reasons, but the most common reason is that market in that particular geography was did not work on that particular day, whereas it was typically, Yahoo has typically treated it as a kind of a working day. Now you can very well look at plotting, right? You can very well think of doing a kind of a plotting of every column or any column. So if you look at the daily adjusted closing price, so this is how the Bitcoin has fluctuated, the price wise. So somewhere it has even touched 60,000, 65,000 kind of mark during 21, 22, right? And again, right now it has fallen. So you could see that there has been a very heavy volatility associated with the Bitcoin pricing. Probably, if you have looked at the typical stock, any stock, Reliance or Infosys, you may not find some such kind of pattern. But definitely, this is something that you are finding with Bitcoin. Similarly, if you want to do a similar exercise for the monthly data, probably that would be a little bit smoother. The daily data would be very, very rough with so many points, whereas the same Overall, the pattern might remain the same in a monthly data, but the data is a little bit more smoother. Now, similarly, we can also look at the volume, right? We'll also take up one more plot as with respect to the daily volumes instead of the closing or the adjusted closing price. I can very well look at the volume. Okay, so you could see that initially the traders in Bitcoin were quite lesser, but I think off late the numbers have increased. Somewhere in 2021, the number of transactions that happened has gone up quite drastically, and again off late there has been kind of stability, but still a little. I mean, has come down, but still there has been a lot of volatility. There are some days where the volumes are much higher compared to until 2019. So I think from 2020 onwards, we could see that the trading in Bitcoin has actually gone up. Now, sometimes people are more interested in finding out the returns rather than the price. People are more interested in seeing the percentage change in price. So you can very well think of computing the returns, right? You can very well think of computing the returns, and you can returns is nothing but the change in percentage change from one day to the other day. P2 minus P1 by P1. That is where you are calling as the change in return. So we can very well go with a daily change in returns. So I take the percentage change, right? So I will take the percentage change in returns, and I will take only these two columns. Probably I'll call it with a different name so that I'll not disturb the original data. Okay. So I could see here, these are the prices and these were the returns. So initially the returns were like 0.8%, minus 0.2%, minus 0.7%, plus 0.7%. So the values have been much lower initially. Whereas of late, if you really look at, right, of late, if you really look at the Bitcoin, you could see there are a few days where, okay, you could see here it's 1.8%, minus 3%, 0.4%, again 3.9%. So you see some days are very highly volatile, some days where the returns have changed quite drastically compared to the previous day. And sometimes what we also say is, instead of taking the returns in the above manner, where the returns were taken more as P2 minus P1 by P1, which are otherwise called as arithmetic returns, I can very well take the return as logarithm of P2 by P1. I'm not going to dwell into why this. Probably this has a lot of arithmetics. I mean, this has a lot of time series. I mean, especially if you are using multi-period, right? So a lot of arithmetic operations, a lot of theoretical sanctity is there when you are computing the return using this method. So that is the reason I have also gone ahead with computing the log returns, right? Assuming a kind of a continuous compounding. So I can very well look at whatever the returns that I get. So which is nothing but, if you really look at this, if I take log P2 by P1, minus 1 and I just do a plus 1. Right? So this P2 by P1, whichever came as arithmetic return, I do a 1 plus of it, then it becomes log P2 by P1, which is, so that is what I have done here. So I have computed the normal arithmetic returns, I added 1 and I took a logarithm. And this is where I could clearly see the logarithm returns are very close to the arithmetic returns, especially for daily data. But the only thing is they would be lesser than the arithmetic return. They would be closer, but they would be lesser, right? So that is something like your geometric mean versus the arithmetic mean, where you will always find geometric mean to be less than or equal to the arithmetic mean. A similar kind of a concept, geometric returns also could be lesser than or equal to the arithmetic return. So you can very well, you can sometimes, the good thing about as I told you, there is a kind of arithmetic sanctity, etc. So if you want to find out the total return, so you have the daily returns, but if you want to find out the total return over the last 10 days, or if you want to find out the standard deviation over the last 10 days, mathematically what you will find is you can easily add up the logarithmic returns for each day, right? Which where you cannot add up the arithmetic returns of each of the days and say that this is the last, this is the total cumulative return over the last 10 days. But you can very well add up the logarithmic returns. You can very clearly see that the sum of the logarithms is nothing but log of the product, which would actually give you the finally end up with the logarithm of the last day, final day divided by the first day. So you can simply add up the arithmetic returns of each of the days. So mathematically, there is some benefit if you are using logarithmic return compared to that of using the arithmetic return. Right? So that's where I can do a cumulative sum as well. So if I am doing a cumulative summation, this is what it is. All right. So this is one side of the story, right? And if I want more stocks also, possibly if I want more stocks to be monitored, I can very well give them as a list, right? I want all the data of Axis Bank, Hindustan Unilever, like this. I want a lot of data. Then you put all of them as a part of one list, and you give the entire list as a part of this YF download, Yahoo Finance download, right? So you can also do that exercise as well. But yes, right now I don't want to get into that. I'm just showing it to you, right? If you want, you can even go ahead and do a kind of a returns also for all the stocks. So you can actually get a big list of stocks, and based on that you can do the exercise. But right now I want to go a little bit more into understanding the distributional properties of the asset prices and the return. Okay. So initially we will look at the descriptive statistics, which we have looked at in various cases earlier. Okay. So probably I would only look at take two columns. I'll not take all. I'll only take adjusted close, and I'll go for return. Only these two columns let me take. If I look at the descriptive statistics, so you see there are so many descriptive statistics, we discussed about it. So 2600 147 observations, but there was one missing value in the returns. So it's better that we first remove that missing value, right? And the mean, yes, this is the mean value of the Bitcoin price. The mean return is around 0.23% per day, which is typically like a positive return. Then you could see the good thing is you look at the upper confidence interval and the lower confidence interval of the returns, you could see that uh, the zero is not contained in this interval. So if zero is not there in the interval, we can see that the mean is statistically significant. So you can very well say that the Bitcoin definitely gives a positive return because this mean is not as good as a zero. The mean is not statistically equivalent to zero. It is a positive value because you don't see the 95% confidence interval containing a zero. However, you look at the daily standard deviation of the Bitcoin returns is around 3.85%, maybe very high compared to that of the typical stocks, right? You could see the interquartile range. You could see mean absolute deviation, coefficient of variance. The range is almost 62%. So we have very high return days to very low negative return days altogether. You could see the maximum return is 25% on a single day. But on one single day, we saw that the Bitcoin has fallen by 37.16%. So the worst was a fall of 37.16%. So the skewness wise, you could see that it's not that heavily negatively skewed. It's very much closer to zero, so which means symmetrically distributed. But definitely the tails are very fat. Tails are fat because the kurtosis is looking like a very big number. And this is the test of normality of the data, the Jark-Bera test. It's a test of normality of the data. The null hypothesis is the data comes from a normal distribution. The alternate hypothesis is the data does not come from a normal distribution. Now, based on those, you see that the p-value associated with the Jark-Bera test is 0, less than 0.05. You reject the null hypothesis and you say that this data does not come from a normal distribution, which means the Bitcoin returns are not normally distributed, and so is the case for Bitcoin prices also. Both the p-values are very much less than 0.05. So neither the prices nor the returns, they come from a normal distribution. And you could also see the median values are there and the various percentiles are there. Obviously, the 50th percentile is same as your median and the various other percentiles are typically given to us, right? So you can very well refer to, possibly what we'll do is I'll just take this as my new DF. Or probably I'll call that as DF1. Okay. So this is what I said. We can do a testing whether the data is normal or not. Now, why do we really require to test whether a data is normal or not? If my data is more normal, then I can very well see that a linear models can quite comfortably be fitted to the data. But if my data is deviating a lot from normal, then probably I cannot think of fitting linear models to the data. Now, this is where what we are saying is you can very well test by using a test called Jark-Bera test. There are various other tests which can use for normality. you talk about Kolmogorov's or Smirnov test, you talk about Shapiro-Wilk test, or we can even talk about Anderson-Darling test. So there are quite a good number of tests which can help us to establish whether my data is following a normal distribution or not. Now, in this case, we are talking about a Jark-Bera test. As I told you earlier, the null hypothesis is the data comes from a normal distribution, whereas the alternate hypothesis is the data does not come from a normal distribution. Okay, so if I really run that, so you could clearly see here, these are the same values that we have got in the descriptive statistics also. You look at the skewness of the closing price is positively skewed, whereas the returns are almost symmetric. Returns do not have a wide negative skewness or something, because you could see that the value is very close to zero. The more the coefficient of skewness is deviating from zero, the more you say that it is deviating from normality, or that it is deviating from symmetricity. So in the skewness for the closing price, we see that the value is 1.312, which is a positive value because it is skewed, it is deviating a lot from 1. But if you look at the kurtosis, you could clearly see here that the kurtosis for returns exorbitantly higher, but the same is going even with the closing price as well. It is 3.6. So the skewness and the kurtosis being higher, whereas in case of returns, only the kurtosis is higher. Overall, the message that is coming out is the data is not coming from a normal distribution. So logically speaking, the may not be the best possible model. Though we are go is, as we have discussed in our learning, is there when did you lose me? When did I get disconnected? I could not realize that. So what was I explaining when I got disconnected? Can someone? Okay. So did I talk about? So I talked about the skewness and the kurtosis. Yeah, normality test. Fair enough. So we could see that the skewness and kurtosis are, for the adjusted close, skewness kurtosis are very much deviating from zero. So the skewness is very much closer to zero, which means there is a symmetricity, but the tails are very fat. The tails are very fat, and that is where we could see that the Jark-Bera test has rejected the null hypothesis in both the cases, and it has mentioned that in both the Bitcoin prices and Bitcoin returns, they are non-normally distributed. And as I have just specified, if a data is non-normally distributed, then though we may use linear models, but they will not be the most effective kind of model. So you may want to really look at some kind of non-linear models. But if I am not aware of non-linear models and I still want to use some kind of linear models, then as a part of the pre-processing of the data, you can do some kind of non-linear transformations on the data, like your Box Cox, EO Johnson. And in case you are able to bring the data into, a normality kind of a mode, after doing that Box Cox or transformation, then you can very well think of using a linear models only to predict. But in this course, we are primarily looking only at the normal, not, we are only looking at the linear models, and that too, one major linear model called the ARMA family of models. And on the same lines, I can very well do, as I told you, there are various other ways of testing whether the data is normally distributed or not. So on the same lines, we have something called omni test, omni normal test. So even the same can give you, possibly it's a different way of computation, but you can very well look at the result is not much different. Right? Both of them, the null hypothesis is the data comes from a normal distribution, and the alternate hypothesis is no, the data doesn't come. Now, what you could clearly see is both the p-values are very much less than 0.05. So you reject the null hypothesis and you say that the data is non-normal. So this is one of the properties that you generally observe with any time series. You can test with any time series whether it is normally distributed or not. So if there is a normally distribution, then probably we can think of working with linear models. It's not that the linear models will definitely give me a prediction, but this is a kind of a direction. So if the data is more normally distributed, then we can say that the linear models are more appropriately suited to model the data. But the more and more we are deviating from normality, then we may go ahead saying that the non-linear models would be more appropriate to model the data. Right? Then the other thing that I can very well think of is I can very well plot. Of course, here I'm plotting both the price and there is no point. So we'll plot the price separately. So if I look at the price, sorry. So if I look at the price, this is how the price is going. And if I look at the returns, this is how the returns are going. So probably in some cases the returns are right. The returns are growing at a much better rate. Okay, I think I have called this as DF1, right? So I think I have to use DF1 everywhere. Okay, so here also I should call it as DF1. So this is the returns. You see no, this is the closing price. Let me just print the DF1 once. It is giving a slight. Okay, DF1 is looking pretty much fine. Yeah, this is the DF1 returns. And probably I can also talk about, I can plot the price as well. So I can very well get the price. I can also get the returns. Okay. Then we'll plot both of these things in two different. We can create subplots and we can plot, or probably we'll plot them in two different cells. So I get the returns here. I get the prices here. So you could see that the returns are looking more stationary in nature. This is what is stationarity. The returns are looking more stationary because at some 2 points, if I randomly take, I see that the mean values are more or less closer. But I don't know whether the variances are constant, but definitely I can say that the means are more or less constant because the value is just fluctuating around a particular zero kind of thing. Whereas if you look at the prices, that is not the case. Here the prices are very low, whereas here the prices are very, very high. So if I take the means of two different points in time, they may not be similar. Then the next thing is look out for the autocorrelation. So in the prices versus the returns, I want to see what is the extent of autocorrelation that is present. Now, this is way, or sometimes we also want to look at stationarity test as I told you earlier. So we will talk about some other important properties. So one is we'll look at whether these two are stationary or not. As I have already told you, the prices are not looking stationary, whereas the returns are looking stationary. I don't know whether they are really stationary or not. How to decompose? Decompose into what? Seasonal, trend, seasonal, and yeah, I'll come to that. So you have a direct function for decomposing. Let me just recollect it. So you can very well go with Just give me a minute. So for all these things, it's a straightforward stuff. There is one command I'm not able to quickly recollect it. So you can very well talk about the decomposition can happen in the additive mode or the multiplicative mode. So in additive mode, you will talk about the level, which is like a constant. Then you have a trend factor, which talks about something on an increasing trend or a decreasing trend. Then there is an adjustment for seasonality, and whatever is remaining is the noise. So normally you have some such kind. In multiplicative, we are just talking about a multiplication of these three. So you'll have a level, which is a constant, then you'll have a trend, then you'll have a seasonality adjustment, and finally it is, yeah. So you can use this function called seasonal decompose, right? So I can simply talk about use this. So we can. So using these two lines, we can do a seasonal decompose. So this is what we are calling as a seasonal decompose. So you could see here, initially, when you are talking about what is happening in a seasonal decomposition is first, there is a trend part that is coming in. The trend part is coming in purely as a kind of a linear regression equation. Here in all these softwares, what happens is the trend is typically a linear regression function that can happen with the previous value. So it's like an auto regression kind of a function, right? Based on that auto regression, whatever the next predicted value comes out by looking at a simple auto regression with time. So time is the independent variable, and the observed values are your dependent variable. Based on that, you will typically find out the trend part of it. Then similarly, for seasonal, what will happen is there is a seasonal decomposition that can happen. So here, because we have taken a kind of a daily data, you will see that for almost you will see that there is a decomposition that is happening by taking some 12 time periods at a stretch. So you could see that these values are typically repeating. You see here, this is 0.101, 0.101 by default. The default seasonality setting typically taken is on a kind of a monthly basis. So which means 12 is the typical frequency that is being taken. So you will find that there is some repetition that can happen. So you could see here there is a minus 27.05, and here also we could see a kind of a minus 27.05. So there is some kind of a repetition that happens with every season. Then whatever is not, so which means initially there is a trend to that, so there would be some constant to that trend, to that a trend is added, to that a seasonality is added or subtracted, and whatever is left is typically residual. So you could clearly see that in some cases the residual is minus and in some cases the residual is plus. So this is where if you are using the residual, then it means you have either handled, you have removed the trend, you have detrended the data, you have deseasonalized the data, and that is what is typically your residual. Now you could typically talk about this residual. We will plot this residual. So you see the residual currently is coming more in this kind of a format. So your price data, which was initially looking like a trend, upward trend or a downward trend, once you have decomposed it, it has actually become something like this. So which looks like it is more and more stationary in nature. So after you decompose the data, split it into its level, trend and seasonality component, and you work only with the residual, you may find that the data will become more and more, I don't say stationary here, but definitely it is moving more closer towards stationary. Would that suffice for us? I think that was what was your question, but just confirm. Okay. So we have plotted. So which means now I don't know whether this data is stationary or not. Definitely, I'm not seeing probably here if I take this block and this block, I'm seeing that the variance may not be constant. So there could be a very heterogeneous kind of variance, and that is where we are using the word called heteroscedastic. So I'm not saying that the data is more homoscedastic here because initially the variance is very in a lower area, whereas of late the variance has been very high. The fluctuations have been very high. But yes, we can use this augmented Dickey-Fuller test to typically test whether our data is stationary or not. Now for that, what is that we say? For stationary augmented Dickey-Fuller test, we say that the null hypothesis is data has a unit root. Of course, I'm not getting into the definition of unit root, right? We have to go with the characteristic equation, then try to find out the roots. So the default null hypothesis is the data as a unit root, and the alternate hypothesis is the data does not have a unit root. So the most common scenario when it does not have a unit root is the possibility of a stationarity, though there could be another interpretation that we can say if it is not a unit root. But most of the common scenarios that I can think of is if it is not a unit root, then it can be treated as stationary. So the null hypothesis, the augmented Dickey-Fuller test carries a null hypothesis of data being a unit root, which means it cannot be stationary, versus the data not being a unit root, which indicates that it could be a kind of a stationary. So what is that we can say? We can run that, and after that I would also try to understand the autocorrelation function and the partial autocorrelation function as well. Now what we could see is we'll first run the Dickey-Fuller test. Right, I'm trying to run the Dickey-Fuller test, augmented Dickey-Fuller test, both for the closing price as well as for the returns. You could see that for the closing price, the p-value is 0.45, greater than 0.05. So I failed to reject the null hypothesis. So I may have to go with the null hypothesis itself, which means I can say that the data is having a unit root. It cannot be a stationary. It need not be a stationary. So the prices, the Bitcoin prices are not stationary per se. Whereas look at the returns, the p value is 0.000, which means it is less than 0.05. If the p-value of the augmented decupolar test for the returns, daily returns is stationary, right? You can very well say, the p-value is less than 0.05, so you will reject the null hypothesis of unit root and you confirm that the data is more stationary in nature. So you could clearly see that the prices are stationary, are not stationary, but the returns are. And how about what is happening with respect to we took the this one. I look at the residual plot and I want to check whether this residual plot is stationary or not. Okay. So we could clearly see that the p value, right, probably will just take only the first two values or we'll take the whole thing. We'll take only the first two values, right? So instead of saying this, I'll call this as residuals. So you could see that the residuals is also not right even after I have decomposed into trend, seasonality, I have de-trended, de-seasonalized, etc. But still, I am not able to make the data to be stationary. So even after doing this, my uh, prices, the Bitcoin prices are still not stationary. Right. So that is one aspect. Then we can also look at the autocorrelation function as well as the partial autocorrelation function. So we will go with the autocorrelation and we would also go with the partial autocorrelation function. Let us see. So we could clearly see here in case of the Bitcoin price, you could see that the autocorrelation is very gradually coming down, very slowly. So there is a lot of persistence that you could see, right? The price wise, the autocorrelation at almost 30-35 lakhs is very much significant. You see that this is a kind of an elliptical region, right, which is talking about your confidence level interval. We are talking about a 95% confidence interval with the lakhs. And obviously, what we are seeing is our correlation is typically, autocorrelation is typically very much outside this 95% confidence interval, which is an indication that very significant autocorrelation is present in the price values. Obviously, the price is not stationary. We have already looked at that. So if the price is not stationary, so first of all, this ACF and PSCF are more and more appropriate when your data is stationary in nature. So in this case, the data is not stationary, but still we wanted to understand. So you could see that the autocorrelations are statistically very significant. But when you look at the partial autocorrelation or autocorrelation in case of returns, I'm not seeing any significant autocorrelation in case of returns here. I don't know, most of the returns are lying within this 95% confidence interval itself. I'm not able to see any returns that are significantly coming out of this 95% confidence interval, right? So some of them may be slightly coming out of that blue shaded region, but they are not that clearly visible. Similarly, when it comes to the partial autocorrelation, you could clearly see that only the first lag is significant. Whereas you look at the autocorrelation, you see that the lags are, so many lags are significant, but when you look at the partial autocorrelation, you only see the first lag is significant, and after that, majority of them are going very much insignificant, lying within that small interval itself. And same is the case with partial autocorrelation function of the returns as well. Right? So at least these are the graphical ways of trying to understand the autocorrelation and the partial autocorrelation. Obviously, in CS2, you might have studied by looking at the autocorrelation function and the partial autocorrelation function, you can very well decide on what order of AR that you should go with, what order of MA you should go with, right? How do you decide on the order depending on where the ACF cuts off suddenly, where the ACF gradually goes down, where the PACF cuts off suddenly, where the PACF gradually goes down. So you might have seen some of such kind of scenarios in your CS2. Whereas here, though I can take the help of all those, but suddenly looking at the graph of a real world data, sometimes it becomes very, very tough to really narrow down on what order of AR or what order of MA that I need to use. So from that perspective, right, one way is we have that auto arima kind of a function. I'll try to use it slightly later. But now even whether the autocorrelation is significant or not, so we have a kind of a statistical test. Many a times, the graphical plot may not give us a very straightforward kind of an interpretation. It becomes more subjective kind of an interpretation. So more common way of establishing whether autocorrelation is present in the data or not can very well be done by a statistical test, which is otherwise called as the autocorrelation based L-Jung box test. So L-Jung box test is typically a autocorrelation based test, right? Especially it's a statistical test which has a null hypothesis of the no serial correlation is present in the data against an alternate hypothesis of a significant serial correlation being present in the data. So this actually computes the presence or absence of serial correlation based on by taking the correlations up to a specific lag. Let's say if you are talking about up to lag 10, which means the last 10 days of data, and to what extent it impacts the overall model. So especially you can take it for 10 lakhs or 20 lakhs, and let us see if I want to go ahead with the L-Jung box test. You see here, in case of prices, the p-values are showing to be 0, which is a clear indication that the null hypothesis is rejected, which means the alternate hypothesis is there is a significant serial correlation present in the data. But as we have initially discussed itself, this data itself is not stationary. The prices data itself is not stationary. So obviously you will expect an uptrend or a downtrend in it. And because it's an uptrend directly, you would only look at some kind of correlation existing, but definitely that may not be that useful unless you make the data more stationary. So that is where probably when you use that model for use that data for developing an ARMA model or something. The automatic ARMA models also, what they do is they internally make the data to be stationary by taking the differences, etc. And only after the data is made stationary, then only the ARMA models are typically fitted. But on the other side, you could see that the returns, they are more and more clearly establishing that there is no serial correlation in the Bitcoin return, which means when there is no serial correlation, then it's a clear indicator that the ARMA model, so it's actually like sounding like a white noise. There is no correlation with any lag. So all the historical lags, the correlations are shown to be statistically 0 because the p-values are greater than 0.05 in all the cases. So there is no serial correlation with any of the lags significantly. So which means just using the historical returns and using an ARMA model, I would not be in a position to predict the future returns. So straightforward it is coming. Using the ARMA model, it is not possible because the linear serial autocorrelation is not observed in the returns data. Only when it is observed, then it means that I can use some model to do the prediction. Just like the way we are seeing here, in case of price, we are observing some kind of serial correlation, but of course, that is primarily because of non-stationarity in the data. But whatever is the information that we have, it is clearly saying that the price data is not serially correlated or is serially correlated. Whereas when it comes to return, there is no serial correlation at all in the return. So when there is no serial correlation, I cannot think of using a kind of a linear model to predict the values, right? So from here, our job is very simple. We can use, so now going ahead, I want to predict the price. I want to develop a model for the price. So what is that I can simply do? I use this function, I use this module or a library called PMD ARIMA. And within that, there is a function called auto ARIMA. So which means it actually does convert the data into stationary, if at all it is not stationary. it will try all the orders of AR rather than trying to look at the graph and based on that graph trying out which value of P and which value of Q are more suitable. That is more for a pen and paper kind of an exercise. Whereas here, what the software typically does is it tries out all the combinations of P and Q, and based on that it will give out the best possible kind of a fit. So let us try both for the prices as well as for the return. Okay, looks like. Okay, somewhere before I do this, let me see if there are some blank values. That is when this kind of errors are bound to occur. Okay, you see, once I remove those blank values, we are getting some kind of outcome. So what we are seeing is in case of the Bitcoin prices, the best possible model ARIMA model is 010 kind of a model. We'll discuss what it is. And whereas in case of prior returns, it is, if nothing is mentioned, then it is called as a 000 model as such. Right? If nothing is mentioned, it becomes a 000 model. Only intercept is there. Whereas in case of prices, even the intercept is also not there, only the sigma squared is there. Now, for that matter, so this is typically called as the ARIMA PDQ kind of a model, right? So probably I'll explain this in our next class rather than trying to hurry it now, right? Sometimes you might be interested both for your CS2 exams or even otherwise, right? So we have a few, I think we don't have too many modules to talk about, right? I have only two more major content to talk about. So we will discuss this in our next class, and then we would go towards understanding our the other concept, the image related. So if everything goes fine, then probably in the next class we can wind up. But if someone wants to discuss a few other topics, you can let me know. Right. Of course, these are like, as we said, this is purely talking about a very basic linear time series models. But definitely, you have many more non-linear, many transforms. So, time series analysis is another area of expertise in itself. So, if some of you are interested in that dimension, univariate, multivariate time series, etc., you can very well focus on that. So, this is just to give you a kind of an initial intro into the same. All right, so I'll stop this session here today because we have reached a very core area where the interpretation might take some time. So, we'll spend the time for interpretation in our next class. In the meanwhile, today, if someone is having questions, we can discuss them. Otherwise, I'll share this sheet and probably you can practice it, because I might think of we might think of meeting on Sunday, I'll confirm it through Ravindra, but probably we might use the Sunday to typically wind up the session. And in case it does not, then probably we'll go up to Monday as well. All right. So any questions from any of you on whatever we discussed today? If there are no questions, then